It was Colonel Paul Tibbets who took war forward into the nuclear age when he dropped a single atomic bomb, known as Little Boy, on the Japanese city of Hiroshima on August 6, 1945, from a B-29 bomber called the Enola Gay. 130,000 people were killed, and of the city's 76,000 buildings, all but 6,000 were destroyed. 3 days later, a second device was exploded over Nagasaki, and Japan surrendered.
The use of the bomb to destroy Hiroshima and Nagasaki was the most powerful imaginable demonstration of the destructive force of the bomb.
The terrible capability of nuclear weapons had been shown for the first time, and there began a scramble by the world's most powerful nations to develop their own bomb. One of those was Britain, and a secret plant was built at Windscale, a remote spot on the northwest coast of England, to manufacture plutonium, the man-made element which gives atomic weapons their terrifying power. But the British reactors, designed and built for the purpose, had one major flaw, and within 7 years of the start of production, would become the site of the world's first nuclear accident.
Windscale was an accident that was waiting to happen.
It was here, at Los Alamos, in the New Mexico desert, that the Manhattan Project, the wartime work to build a nuclear weapon, was carried out in utmost secrecy. It was led by Major General Leslie Groves, a US Army engineer. The chief scientist was J. Robert Oppenheimer. The idea that nuclear fission could be used in the creation of the most powerful weapon the world had seen was first put forward in the late 30s. In Britain, the Maud Committee was set up to investigate the possibilities and reported in 1941. But it was the United States which undertook to build the first atomic bomb, a task it completed in less than 3 years. That it was able to achieve its aims in such a short space of time was a testament to the country's determination, scientific abilities, and industrial muscle. 3 new towns were built. Los Alamos was where the scientific team was based and where testing was carried out, while production of fissile material took place at Oak Ridge, Tennessee, and at Hanford in the Pacific Northwest. The Hanford reactors were designed around a graphite core cooled by water drawn from the Columbia River. Such was the concern over the potential for a nuclear accident that a 25-mile, 4-lane highway was built to allow the swift evacuation of workers. Scientists knew that if the water supply failed, it would be impossible to shut down the reactors before a nuclear explosion. But the pressure to manufacture plutonium was so high that the risk was judged to be acceptable. When the land upon which Hanford would be built was acquired, 1,200 people lived within its 625 square miles. Construction was a massive undertaking, but the speed of progress allowed the first fissile material from Hanford to be delivered to Los Alamos in the spring of 1945. It was eagerly awaited by the scientists, and preparations were made for the world's first nuclear explosion, codenamed Trinity. The device was raised to the top of a 110-foot-high metal tower and tested in the early hours of July 16, 1945. To the delight of Oppenheimer and Groves, it was successful, producing a blast equivalent to 20,000 tons of TNT.
It was very important for the US government that the bomb project should be successful for changing reasons. Initially because they were afraid Germany might get a bomb first, so that became a fact. It was early on a factor in thinking about the war with Germany. Then secondly, when Germany was defeated and the bomb still wasn't quite ready, but nearly ready, of course the whole focus was on the war with Japan. And there, the importance of the bomb was that it would help to bring the war to an end quickly.
When a second bomb was dropped on Nagasaki 3 days after the Hiroshima explosion, Japan immediately surrendered. The destructive power of this new weapon shocked the world, but served also to convince politicians that membership of the nuclear club would bring with it a world status few countries could hope to achieve. Britain had been very much the junior partner in the Manhattan Project, though its scientists had had access to some of the pool of American knowledge. The Soviet Union was aware of what had been going on at Los Alamos through a British spy, Klaus Fuchs. Though at diplomatic level, there was no more than the merest hint of the kind of weapon the United States planned to deploy.
The only thing that was done was that at the Potsdam meeting in July of 1945, after the bomb had been successfully tested in Alamogordo, Truman went up to Stalin after one of the formal sessions and remarked to him that we have a bomb of unusual destructive power. And Stalin apparently said nothing, just nodded his head, maybe said thank you, but in any event, went back, talked to his people, and it was clear he understood that what Truman had in mind was the atomic bomb, because the Soviet Union had very good intelligence about the Manhattan Project.
Post-war Britain was in a much weaker state than it had been before 1939, though it took 2 decades before the country began to come to terms with its new world position. It seemed entirely natural to pursue a nuclear policy, so scientists were set to work creating an independent nuclear weapon, a deterrent in the Cold War with the Soviets. The project had nothing like the money and resources available to the Americans, so an early decision had to be taken over which fissile material would form the heart of the British weapon. The Manhattan Project had hedged its bets by creating 2 production sites, each of which made a different core element. The task of Oak Ridge was to manufacture uranium-235, whilst Hanford created plutonium in its water-cooled graphite reactors. Neither technique was particularly easy, but there were advantages in following the plutonium route, and at first the British government set about looking for a site to house 2 water-cooled reactors, along the lines of those at Hanford. The Americans had realized very early on that such a design carried inherent risks. If the coolant system failed, the pile would quickly become an atomic bomb. So their plant had been sited on a loop of the Columbia River to give easy access to the 25,000 gallons of water a minute needed to keep each reactor cool. But Hanford covered over 600 square miles, and there was nowhere in Britain suitable which met all of the requirements for such a design. So instead, the engineer in charge of production, Christopher Hinton, felt the only feasible solution was to build reactors cooled by air.
Christopher Hinton was extremely resistant to the idea that he should build water-cooled reactors in England, because he knew that the reactors at Hanford were far from safe and that they had deliberately been built in a very, very remote site, and there was no site in England, remote, or in Britain, sufficiently remote, in his opinion, to have a water-cooled reactor safely sited there.
So the decision was made to opt for air cooling, a system previously rejected by the Americans. The enhanced safety offered meant that a site much closer to inhabited areas could be used, and eventually a former Royal Ordnance factory on the Cumbrian coast was chosen. But British scientists were at a disadvantage. Although they had been given access to many of the Manhattan Project's secrets, they hadn't been allowed near the plutonium-producing site at Hanford, and their knowledge of the process was sketchy. Furthermore, the McMahon Act of 1946 forbade American scientists from sharing nuclear secrets with any foreign national. But as time went on, there were informal meetings between British and American nuclear physicists, notably one in 1949 involving Edward Teller. He had worked with Enrico Fermi on the first ever nuclear pile at the University of Chicago. Teller, who went on to mastermind the hydrogen bomb, met with scientists from the Atomic Energy Authority at its Harwell headquarters.
There was a visit from 2 or 3 American scientists, Teller and Wigner. And Wigner, who was a Hungarian refugee scientist, very distinguished Hungarian scientist in USA, and who was obviously the discoverer of Wigner energy, he said that he thought that there was a danger of a fire in one of the British reactors, because he said that as a result of irradiation, you will get energy slowly building up in the graphite, and then, unless you can find a way to release it, you are going to have an explosive situation.
But although the British scientists listened to the warnings from Teller and Wigner, they failed to pass them on to their colleagues at Risley responsible for the design and construction of the Windscale piles. The energy state discovered by Wigner and pointed out to the British in 1949 would prove to be the cause of a fire in the No. 1 reactor 8 years later, when the graphite moderator collected a potential energy from the irradiation process. Wigner's prophetic warning suggested that the release of this energy, unless properly controlled, could lead to just such a conflagration.
Fission produces fast neutrons. The neutrons produce fission, but in the reactors they do it primarily not in their original fast state, but after they have been slowed down by many collisions with nuclei. These collisions with nuclei displace these nuclei. And in a graphite reactor, for instance, quite a number of the displaced carbon nuclei remain stuck in a state different from their lowest, from their equilibrium state. If then, at a later time, the whole reactor is heated to a somewhat higher temperature, then the nuclei from their somewhat higher energy position find back into their original lower position, and in doing so, release the energy that they had contained. That in turn gives rise to an increase in temperature, which of course accelerates the process that I have already described. And so, Wigner said, reactors run at a relatively low temperature. If the temperature is increased, may undergo a process of instability, and this possibility should be taken into account in the design of the reactor.
Within a few months of the conversation about Wigner Energy, a visit to the Oak Ridge plant in Tennessee by the director of the Atomic Energy Authority, Lord Cockcroft, led to a decision which would have a far-reaching effect a decade later. During his trip, a release of radioactivity was found within the site, which was believed to have come from the chimneys of the Clinton reactor, a prototype air-cooled pile similar to the design adopted by the British at Windscale. The release worried Cockcroft, even though American scientists had already rejected a need for any filtration of the cooling air after it passed through their reactor. On his return to Britain, he insisted that the Windscale chimneys be fitted with filters to catch any radioactive particles and prevent their escape to the surrounding countryside. It was a major engineering headache. By this time, construction work was well advanced, and the only place the filters could now be placed was in hurriedly designed galleries at the top of the 400-foot chimneys. Cockcroft's insistence caused much friction.
Construction was very difficult, building a filter gallery that high up, hauling all that amount of material up and doing the construction at that height. And then also, of course, maintaining the filters was very difficult because the big filter pads in the frames had to be regularly changed, and very often they were done in a howling gale above cloud level, and it was a horrendous job.
The first pile went critical towards the end of 1950, with the second following 8 months later. But by now the pressure on the Atomic Energy Authority to begin the production of plutonium was intense. Britain was being left behind in the arms race, and the timetable for the development of an atomic bomb laid down in the overall strategic plan of May 1947 had been overtaken by world events.
The Russians, I think, really surprised the West. They had got a crude atom bomb testable and actually tested it in 1949. Most people seem to think that was 3 or 4 years ahead of when the Americans expected them to do it. The bigger surprise, though, was the development of the H-bomb, because while the United States had developed an H-bomb by about 1952 and tested a crude one, the Soviets came in only a year later. So in that sense, there was a lot of progress on the Soviet side. It took them years to deploy the finished systems, but at the testing level, they were pretty advanced.
With the Cold War growing in intensity, the British desire to move forward could only increase. Every effort was put into making the Windscale piles as efficient as possible to meet the deadline for a first atomic test in 1952. And although the production of plutonium reached its target on schedule, there were some worrying incidents in the behavior of the reactors that year. In May, there had been an unexplained temperature rise in the number 2 pile, and 4 months later, smoke was seen coming from the core of the other reactor following a shutdown. It turned out that the smoke was simply caused by oil particles being blown onto the hot graphite from the cooling fan bearings. But the unexpected temperature rise was a worry for scientists. Consultations were carried out with the Americans, and it became apparent the cause lay in the release of Wigner energy, exactly what Harwell had been warned about 3 years earlier. A month later, on the 3rd of October 1952, the first British atomic test was carried out aboard a ship moored off the northwest coast of Australia using plutonium from Windscale. For the politicians and scientists, it was a triumph. Britain had gained entry to the nuclear club.
Building the bomb seemed just the natural thing. It was one of the great powers, in spite of being greatly weakened by the economic costs of the war. But still, it was a kind of natural thing, and hardly anybody opposed the decision. Of course, it was carried out in secrecy. There wasn't a great public debate about it. It just sprang from a certain assumption that, yes, well, Britain should have the bomb. And the British did, in fact, expect to be the second to develop an atomic bomb, and were very taken aback by the Soviet test, which came in 1949, where the first British test was 1952. And Western intelligence had, in fact, predicted that the first Soviet test would probably be 1953, maybe 1954. So the British then suddenly found that they weren't the second nuclear power, they were now the third nuclear power. And increasingly through the 50s, especially after both the United States and the Soviet Union developed the hydrogen bomb, again, Britain, was then again lagging further behind. So I think the 1950s were a period of some tension in British nuclear policy, because there wasn't a fundamental revision of assumptions saying, oh, we shouldn't have these things at all, we can rely on the Americans, or we don't need them, or they're immoral, or whatever. So the government didn't go that far. On the other hand, it was finding it very difficult to keep up in this race, or to stay in this race, when the United States and the Soviet Union could mobilize such massive resources into not merely developing new kinds of weapons, but building large numbers of them, and delivery vehicles and so on. So I think it was a very difficult period for the British.
Throughout the mid-50s, atomic tests were carried out by each of the 3 nuclear powers. The Windscale piles remained the only production source of plutonium in Britain, and there was heavy pressure on the Atomic Energy Authority Production Group, not only to meet demand for that element, but also for others, such as tritium and polonium, required for the testing of a hydrogen device. So 2 reactors of a new type, cooled by carbon dioxide rather than air, were commissioned next to the existing piles, and construction work began in August 1953. 2 years later, the need for plutonium had become so desperate that a further 6 of these Magnox reactors were ordered. Meanwhile, a system had been developed to deal with the build-up of potentially hazardous Wigner energy in the graphite core of the Windscale piles. After every 30,000 megawatt days of irradiation, it would be released by a process called annealing. Although the technique occasionally threw up a problem, generally it worked well. But then, in October 1957, there was the accident scientists feared most. During the 9th anneal, the worst-case scenario, predicted in 1949 by Wigner and Teller, came about. The number 1 pile caught fire. By the beginning of October 1957, 8 anneals had been carried out to release stored Wigner energy from the 2 piles. But scientists had noted that some had been less than fully successful. Occasionally it was difficult to balance what had been described by Edward Teller as the Wigner instability while the anneal progressed. And despite the opening of the Calder Hall reactors the previous year, there was still a tremendous pressure on the piles to produce plutonium along with a growing number of isotopes for research work. There had been a further 13 British atomic tests since Hurricane in 1952, and the first trial of a thermonuclear device was scheduled for the following month. The government was enthusiastic about the status and world standing nuclear weapons conferred. The previous July, Prime Minister Anthony Eden said, "It is on the thermonuclear bomb and the atomic weapons that we now rely not only to deter aggression, but to deal with aggression if it should be launched." Things seemed to be going well in the military programme, but unbeknown to those who controlled the Windscale piles, the warnings of Teller and Wigner, warnings which at the time had been largely ignored, were about to lead to the world's first major nuclear accident. On the 7th of October 1957, the number 1 pile was ready for the 9th anneal. Just before midday, its cooling fans were shut down, and the first of the control rods were run out to introduce nuclear heating into the lower part of the pile. It was this process of heating the graphite which allowed the displaced carbon atoms to return to their normal position, an action which itself introduced a further heating effect. In the early hours of Thursday the 10th, a monitoring device on the weather station roof showed an increase in radioactivity, but it wasn't until a second, larger release that the operator's suspicions were aroused. It coincided with a further rise in the pile temperature, and it was obvious to all that number 1 pile was in serious trouble. When 4 channels were opened up to eject the uranium fuel rods, they were seen to be glowing bright red. There could be no doubt now that the pile was on fire.
The decision to look into the reactor was taken by a man called Tom Hughes, a colleague of mine for many years, sadly with us no longer, and he was second in command to me on the operations side. I was second in command to Davy overall, and he made the decision, quite a brave one, to have a plug pulled out and look into the reactor. And this was to look at a channel where a thermocouple was showing an increasingly high temperature and had been doing for about the last 48 hours. And he didn't see flames, but he saw 4 channels of fuel elements. Each plug you pulled out gave access to 4 channels of the fuel elements, and they were all, the ends of the ones he could see were all glowing red.
So Tom Tewey set off to drive to Windscale to assess the condition of the number 1 pile for himself. Wearing a mask and air bottle, he climbed the 80 feet to the top of the reactor building to see exactly what was going on inside.
From the roof you could look down through 4 inspection holes. And I went up there and looked down, and there were no flames coming out of the back of the reactor at that time. But there was a dull red glow. And during the night I climbed up several times, and flames began to flicker out of the channels, and they were quite modest to start with, but eventually there was just a raging inferno at the back of the reactor, and the flames were impinging upon the wall across what was called the water duct. There was we pushed fuel out of the horizontal channels in the reactor, and they fell down into skips which were underwater. Well, the wall on the other side, flames were impinging upon this, And I remember that one of the civil engineers had said to me that if that wall exceeded 600 degrees centigrade, the roof on which I was standing could collapse, which wasn't a very pleasant thought, but I didn't really believe in.
Tom Hughes had already discharged some of the uranium cans around the fire to try to stop it spreading. Chewie decided an attempt should also be made to eject those at the heart of the fire by pushing them out through the back of the reactor using scaffolding poles. But they refused to move, however hard they were pushed.
When these were pulled back onto the working area, the charge hoist, they were red hot. And on one occasion, when this was happening and a pole came back, there was also molten metal dripping off the end of it, which had to be molten irradiated uranium. And of course this was causing a big radiation problem on the charge hoist itself.
The situation was critical and called for immediate action to bring the fire under control. The problem was, how could this be achieved? There was a great deal of discussion about the options available, but at the forefront of everybody's thinking was an overriding need to exercise extreme caution to avoid increasing the spread of radioactivity.
Well, the nice thing to do would be to have large quantities of inert gas to try and feed that in, but then feeding it in wasn't going to be easy anyway. And we discussed the use of carbon dioxide. It so happened that a tanker had come into Calder Hall that day with 25 tons of liquid carbon dioxide, so that we had plenty of it. But I had done some experiments at the fuel plant down at Springfields, trying to put out hot metal fires with different types of extinguisher, including carbon dioxide. And carbon dioxide had no effect. The only other thing that we had available was water. And we were not too enthusiastic about putting water onto burning graphite because you can produce a mixture of carbon monoxide and hydrogen, which under certain circumstances can be explosive.
So carbon dioxide was tried first. A hose was set up on the charge hoist to deliver the gas directly into the burning channels. It was a hazardous task, requiring the operator to be right up against the face of the reactor so the CO2 could be delivered and its effect monitored. But the results were disappointing.
And it had not the slightest effect. Just went on burning as merrily as ever. So carbon dioxide wasn't any good, even if we had a means of delivering it in large quantity, which we didn't. So the only thing we were left with was water.
A hose was wired to a scaffolding pole to allow the water to be delivered into the burning channels. Chewie listened anxiously for any signs of a hydrogen reaction as the pressure was turned up to maximum.
And I went up to the top of the reactor, once again for the umpteenth time, and looked down the back, and there the water was, most of it was shooting straight out the back of the reactor, and as far as I could see, making absolutely no difference to the fire. So I had the pressure reduced so that the water at least was sinking in through the graphite blocks onto the fire. But it wasn't the water on its own that put the fire out. It was eventually shutting down the cooling fans that had to be on if men were working on the charge hoist, on the working area. The ventilation system was such that if you didn't have the shutdown fans running, then you could get radioactive contaminants coming back from the reactor into the working area. With the shutdown fans on, the airflow was from the working area into the reactor. So we had this horns of an enormous dilemma, a raging inferno in the heart of the reactor, and yet we were supplying air to it.
The operators were fighting hard to cope with a situation for which they had never been trained. But once the area was evacuated and the shutdown fans turned off, it seemed at last that the battle to put out the fire was being won.
And I was up then on the top of the reactor looking down the back, and the effect was dramatic. I could just see the fire dying away. The flames were licking against the wall across the water duct, and I could see them actually dying back. And I went up and inspected several times, and the water went on at about, well, just before 9 o'clock in the morning. And by noon I was satisfied that the fire was out.
Whilst the battle was going on inside the pile building to fight the fire, health physicists had begun to assess the dangers caused by the release of radioactivity. There were 3 ways in which the population outside the plant could be affected: by external radiation, inhalation of radioactive material, or through the food chain. It was quickly realized that the biggest danger came from the ingestion of iodine-131, a radioactive isotope with a half-life of about a week. Its intake would lead to an increased likelihood of thyroid cancer, and children were the most vulnerable.
The route from deposition on ground, through grass to the cow, to milk, to child, is a very effective route. A cow covers a great deal of area, grazing, and it collects the iodine from a big area, concentrates it in the milk, and then children, young children, if they're drinking cow's milk, then get a substantial intake. So we were very much concerned with making sure that the milk that was significantly contaminated didn't get to these children.
In retrospect, it's astonishing there was no calculated safety limit at the time for the intake of iodine-131. If anyone had given thought to the consequences of an accident at the Windscale site, no research work had been done in Britain to give scientists a baseline from which they could operate. In the United States, the minimum distance between plutonium factories like Hanford and surrounding populations was laid down in the siting requirements. But in Britain, the agricultural areas of West Cumbria went right up to the Windscale fence. So during the night, a small group began the task of working out what a safe limit for iodine-131 in a child would be. And it was using these hastily calculated figures that the area of worst contamination was defined. Milk from farms within it was disposed of, largely by dumping it in the sea, and fresh supplies were brought in from outside.
The whole area was about 200 square miles, and at the peak areas, which was just slightly to the southeast of the Sellafield site, figures in milk went up to about 10 times the figure we'd set as a trigger level. So we needed to act, there was no doubt.
In the area around Windscale, there was little alarm. The operation to replace contaminated milk with supplies from elsewhere worked effectively, though gradually the size of the affected area was increased. News of the milk ban, along with initial details about the fire, was released at a press conference the following Sunday. The reaction was muted, and although restrictions on milk supply continued for a little over a month in total, the greatest concerns seemed to come from those living away from the immediate area.
Basically, the problem got worse, the public relations problem got worse, the further away you got from Sellafield. And the peak problem was undoubtedly where people living in the south had got children in boarding schools close to the area. And they were certainly very worried. But generally speaking, the people in the area weren't, because they could see life was going on in the ordinary way.
Now that the fire in number 1 pile was out, the next concern was to stop the possibility of any further spread of radioactivity from the pile chimney. The filter gallery, for which Cockcroft had been so criticised for insisting upon during construction, they'd become known as Cockcroft's Follies, had stopped the escape of some radioactive particles. But there was now a worry that high winds could dislodge them and spread them around the countryside. A way of preventing that had to be found.
So there was a committee meeting set up, and I couldn't believe my ears with the sort of things that were being talked about. And the most fancied approach was to get 3 helicopters and make a lid. And with these 3 helicopters, carry the lid up and put it on top of the chimney. Well, I don't know how long this would have taken, but I thought, well, there's an easy way of doing this. So I got a hold of the chief engineer and I said, look, is it possible to get men up outside the chimney on the platform that's formed by the filter house itself, and to get some pipes over the top and to pump some really heavy oil on top of these filters? And he thought about it and he said, yes. I said, all right, let's do it. And that's what we did to seal in the radioactivity.
Sir William Penny chaired a hastily put together board of inquiry into the causes of the fire. It took just 2 weeks to produce a report, and its findings seemed straightforward. It was most likely, they said, that the fire had been caused by the use of excessive nuclear heating during the operation to release Wigner energy from the graphite. This had caused one or more of the aluminium cans containing irradiated uranium to burst. The uranium had then oxidized, releasing more heat, and this, combined with the heat generated by the Wigner energy, had led to the fire. However, the inquiry couldn't rule out an alternative possibility, that it had been a lithium-magnesium alloy rather than a uranium can which had burst. It was felt that prompt and efficient action had been taken, and that it was most likely there would be no harmful health effects. Penny said he had felt it important to report quickly because of public anxiety.
The view of the Atomic Energy Authority was that though it didn't look too wonderful, the thing to do was to bite the bullet and publish the report in full, come clean about it. But and they recommended that. And the Ministry of Defence actually said there is no reason for this to be a secret report. But the Prime Minister, for these political reasons, which were so overwhelming in his mind, said, no, this report could not be published in full.
The report was studied by the Atomic Energy Authority, which accepted that instrumentation on the pile had been inadequate. There simply were not enough thermocouples, the devices which measured spot temperatures in a number of the channels, to give operators an accurate view of what the reactor was doing during a Wigner release. A subsequent re-examination by Sir John Hill, published in January 1958, cast doubt on the uranium cans being the probable source of the fire. He showed that the lithium-magnesium cans, for which the pile had not been originally designed, failed at a much lower temperature than those containing uranium. But what neither Hill nor the Penny inquiry were ever told about was an earlier fire in an oven used to test the fuel rods before they were put in the reactor. 40 years on, Tom Tuohy spoke publicly for the first time about a previous accident he helped cover up, which he feels confirms Penny's view.
One of the tests that was done both at Springfield and then repeated when the fuel was received at Windscale was to heat the fuel elements for 48 hours to a temperature of 300 degrees centigrade, which was about, 50 degrees lower than the temperature you expected to operate them at in the reactor. And this was done in ovens, and 2 tons of fuel was put into each oven for 48 hours. And to our horror, one morning when an oven was opened, the whole fuel mass was on fire. Now this was at a temperature, as far as we know, because there was no evidence that the oven had behaved in any improper manner, less than we would normally be operating the fuel at in the reactor. Now, I'd forgotten all about this when I was interviewed at the Court of Inquiry, chaired by Sir William Penny. But looking back on it now, I think that this is something of really quite considerable significance. And as far as I'm concerned, it enhances the view of the Court of Inquiry that the fire almost certainly started in the uranium fuel itself during the Wigner release.
Looking back from 4 decades on, it's much easier to see the Cold War period in perspective. Britain had suffered because of the Second World War in ways it would only later fully realize and accept. There remained a government view that the country could continue to play a dominant role in the world and still had the economic strength to develop independent nuclear weapons and their delivery systems. It had been an astonishing act for British scientists to design a nuclear weapon in such a short space of time, without access to the key features of the pool of knowledge accumulated by the Manhattan Project. Though there were suspicions the Americans had provided some help, despite the straitjacket of the McMahon Act. It's difficult to quantify exactly what the nuclear program cost Britain, but it's undoubtedly true that the environmental cost of the 1957 fire would have been much greater had Cockcroft not insisted that the filter galleries be built on the pile chimneys. It's ironic that this insistence was based not on sound scientific judgment, but on the misinterpretation of an American accident. The site emergency at the Oak Ridge nuclear plant, which had inspired Cockcroft's demands, had been attributed at the time to releases of uranium particles from the chimney of the Clinton air-cooled reactor. Only later was it realized they had come instead from the nearby chemical separation plant. But for that error, contamination of the Cumbrian countryside could have been much worse. But perhaps the overriding question about the background to the Windscale fire is whether Britain, at the end of a long and costly war, should have gone ahead with a nuclear weapons program at all.
I think that it's an absolutely understandable decision. It's hard for me to imagine that the decision at the time it was taken and the context it was taken could have been different. But I think in retrospect, one could argue that it was actually a mistake, because what it did was actually make it more difficult for Britain to readjust and rethink its foreign policy, given its new kind of status in the world, and that the nuclear project became a symbol of what was increasingly an outmoded position in the world.
It would have been difficult to imagine a more embarrassing time for the fire to have happened. Britain had only recently embarked on the world's first nuclear power program, and the Calder Hall station, next door to Windscale, although designed and built to produce plutonium, had been opened by the Queen in a blaze of publicity about its generating capability only the previous year.
It is with pride that I now open Calder Hall, Britain's first atomic power station.
This new source of power had been received enthusiastically, amid claims it would make electricity too cheap to meter.
To have had something casting such serious doubt on the safety of the nuclear power stations, which were going to be built all over the country, was really pretty shattering. And the other reason that it was such a very unfortunate time for them was that the Prime Minister, who was determined, as the sort of jewel in the crown of his premiership, that he was going to achieve the nuclear partnership with USA that the British had so long been trying to re-establish ever since the war, and he saw it within his grasp, and he was just going off in October 1957 to Washington for crucial talks with Eisenhower, which he thought were going to lead to the restoration of collaboration.
But if the fire caused political embarrassment because of the civil power program to come, its effect on military needs was negligible.
I think the first 2 Calder reactors were already operating. There are four power reactors at Calder Hall, but of course they can also be operated in such a way as to produce military plutonium. And that really was their purpose. The power production was a sideline to show that it could be done, and it has been done very effectively, as they've been operating now for 40 years. So the loss of the output from the Windscale reactors wasn't such a bad thing from the military point of view. From the point of view of producing power, it didn't really make any difference, because no one was ever going to build another reactor like the dear old Windscale piles. They were the biggest hot air machines that man has ever invented. We blasted cold air in at one end and hot air up the chimney.
The month after the Windscale fire, the British exploded their first hydrogen device at Christmas Island. They had finally reached their goal, 5 years after the Americans, and despite losing ground to the Russians. Along the way, in such pioneering work, it was inevitable that a level of technical ignorance and the pressure of political desire would combine to create a situation where safety was less important than it should have been.
But one has to appreciate in the first 15 or 20 years of the nuclear age, and maybe to some extent now, people were rather easier with safety. Partly because of the need to speed things up, partly because there wasn't yet the clear understanding of how dangerous radiation was. I mean, that really was something which developed in radiobiology in the 1950s and 1960s. And of course, you've also got to appreciate that these were the Cold War years. By 1948, the Americans had already got 50 usable atom bombs. So they set up a very big production process, as did the British later on. So, to some extent, the shortcuts taken during the Second World War were not dissimilar to the shortcuts taken in the late 40s and 50s, only this time it was because of the Cold War. And I think essentially safety, one has to say, took second place in many cases. You see it especially in the way in which the weapons were deployed. I mean, now the idea of having planes flying more or less continuously with nuclear weapons on board, as was routine in the 1950s, seems almost unthinkable. But then the ideas about safety were frankly a lot cruder.
Yet the man who warned the British of the dangers they faced is sanguine about the fire. Dr. Edward Teller has been a lifelong supporter of nuclear energy. He argues that the value of the lessons learned was more than worth the economic and human costs involved.
Windscale will be remembered as something that added to our concrete knowledge without a really dreadful expenditure and connected with real safety of human health.
The rush to build an atomic weapon and the decision to use air-cooled reactors were the real causes of the Windscale fire. It's so easy to look back over the decades and say it should never have happened. But the political climate which existed after the Second World War was very different from today's. The Soviets were perceived as a real threat to the West, and Britain was determined to maintain its place in the world pecking order. If the Americans had been more cooperative, the Harwell scientists had paid more attention to the warnings of Teller and Wigner, or the potential sites for water-cooled reactors had been more suitable, things might have turned out differently. But given the set of circumstances which existed, the result was inevitable.
There was only one way to stop the fire happening, and that was to shut down the reactors. Once we had a situation where we knew that with a Wigner energy release you could get a very rapid rise in temperature. If you were going to operate the reactors in an abnormal way, with an abnormal control rod patterns, which your instrumentation was not designed to cope with, then you were running a risk. And the only way to avoid that would have been not to operate the reactor.